So, to begin with, this is Hyperbolic Functions by James McMahon. This is actually kind of old. It's about a century old, and not exactly really set up well right now. Maybe it'll work if I have my drawing pad on my lap, but so hyperbolic functions. This is James McMahon. If you look inside, if you actually had the book, you can't really find this on Amazon anymore. I don't know where I found it, but I bought it. And yeah, it's 1906. The guy was a professor of mathematics in Cornell University. This would be the 4th edition. Apparently it's enlarged. And, well, this is a reprint. It's been reprinted, so. The back side has just the author's preface and whatnot. The ISBN is 978-1495498893. And, yeah. The only use that this ever really pops up is in Calc 2, the second semester, and just kind of like a silly kind of mathematical trick or something like that. But there's nothing that's actually like focused on it until you get into a graduate level, and it's ridiculous. I mean, college is already overpriced. Community college is okay, but universities, it's just insane. So the editor's preface. The volume called Higher Mathematics, the first edition of which was published in 1896, contained 11 chapters by 11 authors, each chapter being independent of the others, but all supposing the reader to have at least a mathematical training equivalent to that given in classical and engineering colleges. We don't have engineering colleges anymore, I think. Or classical. They're all just universities. Anyways, the publication of that volume is now discontinued, and the chapters are issued in separate form. In these reissues, it will generally be found that the monographs are enlarged by additional articles or appendices which either amplify the former presentation or record recent advances. Quite honestly, this is actually dated 1905, and I don't think there has been any advances in the last century. Continuing on, this plan of publication has been arranged in order to meet the demand of teachers and the convenience of classes, but it is also thought that it may provide advantages to readers in special lines of mathematical literature. It is the intention of the publishers and editors to add other monographs to the series from time to time, if the call for the same seems to warrant it. Among the topics which are under consideration are those of elliptic functions, the theory of numbers, the group theory, the calculus of variations, and non-Euclidean geometry. Hyperbolic functions generally are non-Euclidean geometry. Anyways, possibly also monographs on branches of astronomy, mechanics, and mathematical physics may be included. It is the hope of the editors that this form of publication may tend to promote mathematical study and research over a wider field than that which the former volume has occupied. December 1905. And of course, in the last 100 years, especially after World War II, nothing has been done. Everything has just turned into a degree mill. And sure, you might be able to make calculations and do fancy stuff on the computer, but you're still causing bridges to fall. You shouldn't be. You should be thinking a little bit. Testing prototypes. Actually doing real prototypes. And testing it in real situations. Yes, you can try and test all these random things, But you have to make sure that you have an idea of what you're doing. Look at the Tacoma Bridge. You couldn't have thought to have tested whatever it was that caused it? Oh no, we have to wait until the real thing is built, and then, what was it, like a month later it destroys itself? Author's Preface. This compendium of hyperbolic trigonometry was first published as a chapter in Merriam and Woodward's Higher Mathematics. There is a reason to believe that it supplies a need, being adapted to 2 or 3 different types of readers. College students who have had elementary courses in trigonometry, analytic geometry, and differential and integral calculus, and who wish to know something of the hyperbolic trigonometry on account of its important and historic relations to each of those branches, will, it is hoped, find these relations presented in a simple and comprehensive way in the first half of the work. Readers who have some interest in imaginaries are then introduced to the more general trigonometry of the complex plane, where the circular and hyperbolic functions merge into one class of transcendents. Transcendents are pretty much a class of their own. Like, you have the integral, I believe, of e to the x, and the x is squared. So x to the squared, and that's the power which e is taken to. And if you integrate that, that's technically a transcendental function. And so transcendent would probably mean that we don't necessarily know what it's supposed to turn into. Or it's pretty much like fundamental. There's no, I think pi might be transcendent. I'm not quite sure. It's obviously irrational because it doesn't have a stopping point. And the only way that you can truly express it is just as pi. Anyways, the complex plane, the more general trigonometry of the complex plane, where the circular and hyperbolic functions merge into one class of transcendents. The singly periodic functions having either a real or pure imaginary period. For those who also wish to view the subject in some of its practical relations, numerical applications have been selected so as to illustrate the various parts of the theory and to show its use to the physicist and engineer. Appropriate numerical tables being supplied for these purposes. With all these things in mind, much thought has been given to the mode of approaching the subject and to the presentation of fundamental notions, and it is hoped that some improvements are discernible. For instance, it has been customary to define the hyperbolic functions in relation to a sector of the rectangular hyperbola, and to take the initial radius of the sector coincident with the principal radius of the curve. In the present work, these and similar restrictions are discarded in the interest of analogy and generality, with a gain in symmetry and simplicity, and the functions are defined as certain characteristic ratios belonging to any sector of any hyperbola. Such definitions, in connection with the fruitful notion of correspondence of points on conics, lead to simple and general proofs of the addition theorems, from which easily follow the conversion formulas, the derivatives, the Maclaurin expansions, and the exponential expressions. The proofs are so arranged as to apply equally to the circular functions, regarded as the characteristic ratios belong to any elliptic sector. For those, however, who may wish to start with the exponential expressions as the definitions of the hyperbolic functions, the appropriate order of procedure is indicated on page 25, and a direct mode of bringing such exponential definitions into geometrical relation with the hyperbolic sector is shown in the appendix. December 1905. So with the contents, there's 40 articles instead of chapters. It's 40 articles. There's 4 tables, and it looks like 2 appendices and an index. So Article 1, Article 1 is the correspondence of points on conics. 2. Areas of corresponding triangles. 3. Areas of corresponding sectors. 4. Characteristic ratios of sectorial measures. 5. Ratios expressed as triangle measures. 6. Functional relations for ellipse. 7 is functional relations for hyperbola. 8 is relations between hyperbolic functions. 9. Variations of the hyperbolic functions. 10. Anti-hyperbolic functions. 11. Functions of sums and differences. 12. Conversion formulas. 13. Limiting ratios. 14. Derivatives of hyperbolic functions. 15. Derivatives of anti-hyperbolic functions. Anti would be inverse. Guessing, but I'm pretty sure that's it. Anyways. 16. Expansion of hyperbolic functions. 17. Exponential expressions. 18. Expansion of antifunctions. 19. Logarithmic expression of antifunctions. 20. The Gudermannian function. 21. Circular functions of Gudermannian. 22. Gudermannian angle. 23. Derivatives of Gudermannian and inverse. 24. Series for Gudermannian and its inverse. 25. Graphs of hyperbolic functions. 26. Elementary integrals. 27. Functions of complex numbers. 28. Addition theorems for complexes. 29. Functions of pure imaginaries. 30. Functions of x plus, I'll probably say I, because that's typically how you say the complex numbers. Functions of x plus I times y in the form x plus I times y. Maybe I should be saying IY, but whatever. 31, the catenary. 32, the catenary of uniform strength. 33, the elastic catenary. 34, the tractory. 35, the luxodrome. 36, combined flexure and tension. 37, alternating currents. 38, miscellaneous applications. 39, explanation of tables. Then we have the four tables. Table 1, hyperbolic functions. Table 2, values of the way to say the hyperbolic functions is you have COSH, and that's cosh. And then for hyperbolic sine, I think it's sinh. I think it's like cosh and sinh is how we were saying it. And I mean, like, how else are you going to say it? You don't want to say cosine or sine. Hyperbolic sine, hyperbolic cosine, and that's fine, but cosh and sinh are pretty good. So, table 2, values of cosh, x plus iy, and sinh, x plus iy. Table 3, values of, it looks like g, which is the Gudermannian function, whatever the value is coming from that, and it's going to be the times the derivative of u. Like, you have the variable u, and then you have the derivative of that, so g du. And it looks like theta with a degree symbol. That could be theta, like angles and degrees, I'm not sure. Number 4, values of g du, log sinh u, and log cosh u. The appendixes, there's two of them. First appendix is historical and biographical. Second appendix is exponential expressions as definitions. And the index. So, continuing the actual main text of the book, hyperbolic functions is how it starts off. Article 1, corresponsive points on conics. To prepare the way for a general treatment of the hyperbolic functions, a preliminary discussion is given on the relations between hyperbolic sectors. The method adopted is such as to apply at the same time to sectors of the ellipse, including the circle. And the analogy of the hyperbolic and circular functions will be obvious at every step, since the same set of equations can be read in connection with either the hyperbola or the ellipse. There's a asterisk here for a footnote. And the footnote says, the hyperbolic functions are not so named on account of any analogy with what are termed elliptic functions. The elliptic integrals and thence the elliptic functions derive their name from the early attempts of mathematicians at the rectification of the ellipse. To a certain extent, this is a disadvantage. Because we employ the name hyperbolic function to denote cos u, sinh u, etc., by analogy with which the elliptic functions would be merely the circular functions cosine, phi, sine phi, etc. Greenhill, Elliptic Functions, page 175. And that's probably in the historical and biographical appendix. But returning back to the first paragraph, it is convenient to begin with a theory of correspondence of points on two central conics of like species, i.e., either both ellipses or both hyperbolas. To obtain a definition of corresponding points, let O sub 1 A1, A sub 1, O sub 1, B sub 1, these are going to be line segments. So O sub 1 to A sub 1 and O sub 1, B sub 1 to B sub 1. So that would be kind of like part of a triangle almost. But of course it's not going to be a triangle because this is probably going to be a hyperbola, I'm not sure. Be conjugate radii of, this looks like alpha centric conic, and O sub 2, A sub 2, and then O sub 1, O sub 2, B sub 2, conjugate radii of any other central conic of the same species. Let P sub 1, P sub 2, and P sub 2 be 2 points on the curves, and let their coordinates refer to the respective pairs of conjugate directions be a 2-point pairs. So we have that does not work. Whatever. I want a pen. Pen. Oh, damn it. Not a pencil, I want a pen. This might work. Download this custom G pen. I need to sign in for that. Yeah. Looks like I'm using a pencil. That's not exactly what I'm looking for. might need to switch over to Paint for now. I'm not sure. It's also super light. Oops, no. This isn't gonna work. I'm opening up Paint. Shit. Alright, and then I also made sure that I can at least have the full range. So, anyways, we're going to have 2 points. We have x1 and y1. Oops. x1, y1, and then x2. First time with a drawing pad, really. I mean, kind of, not really. I've used the drawing pad before, but x sub 2, y sub 2, and then after we have these respective pairs of conjugate directions, then by analytic geometry we have 2 different things that we can say. So we can say for the first one, you have x sub 1 squared, that's divided by a sub 1 squared. This is plus or minus. Pretty sure if it's plus, then it's a circle, but if it's minus, I believe it is a hyperbola. And then you have y sub 1 squared divided by b sub 1 squared, and we want this equal to 1. As for the second one, we have so yeah, that x sub 2 squared divided by a sub 2 squared plus or minus y sub 2 squared and b sub 2 squared. This is equal to 1. So this is the first kind of set of equations. So whatever. Now at the points p sub 1 and p sub 2 be so situated that, oh, so yeah, let's see, this is p sub 1, and this is p sub 2. Now the two points are situated such that I guess they're on top of each other almost at these points. These are probably the focal points. It's been a while since I actually dealt with this stuff. But you have x sub 1 divided by a sub 1, and this is equal to x sub 2 divided by b sub 2, or a sub 2. B goes on to the y. And then you're going to have y sub 1 divided by b sub 1, and that's set equal to y sub 2 divided by b sub 2. The equalities referring to sign as well as magnitude. Then p sub 1 and p sub 2 are called corresponding points in the two systems. Now we have some random q. Not that one. If q sub 1 and q sub 2 be another pair of correspondents, then the sector and triangle P1, P sub 1, O sub 1, Q sub 1 are said to correspond respectively with the sector and triangle P sub 2, O sub 2, Q sub 2. These definitions will apply also when the conics coincide, the points P sub 1 and P sub 2 being then referred to any two pairs of conjugate diameters of the same conic. In discussing the relations, I'm going to draw these really quick. So there's a few different figures that are given, and so this is probably a hyperbola. Get that, and just imagine I draw like straight lines. So this point here is going to be a sub 1. Over here is O sub 1. This one up here is B sub 1. There's going to be something over here that goes all the way down through there. The point here is not going to be labeled, but there's going to be, this is our original point, the P sub 1, that we're talking about with all these different other kind of points. And this is M sub 1, and then A sub 1 is already there. There's also going to be a Q sub 1. And then let's see. Go ahead and box this off. There's also this bad boy. And you have B sub 2 and O sub 2. This cuts over to A sub 1. Then you have, these are actually supposed to be parallel. So you have from P sub 2 cutting through M sub 2. Over here you have another one that goes into Q sub 2. So this is Q sub 2. This is A sub 2. This one over here is M sub 2. Yeah, this is O sub 2 over here. B sub 2. And P sub 2. Quick check, looks like I have everything. There was no mention of M, I believe. Whatever. Box this one off. Oops. Did not realize that there's a button on here. And yeah, those are the first two. And then these bastards. Go and move this guy. And then this other hyperbola, you got from P sub 1 over here. Imagine that's a straight line coming down. It crossed through M sub 1 over here. Then coming out this way, you hit O sub 2, which branches off to O sub 1, which branches off to B sub 1. B sub 1 here, O sub 1. This up here is P sub 1. No one cares about the little point at the bottom. Then over here we're going to be making a triangle. And this is going to cut over past A sub 1 into M sub 1. This guy right here is M sub 1, and then this is A sub 1. And then from here we cut down into Q sub 1. So, yeah, you have your POA, well, as well as POM. That looks like two triangles that you can form right there. I'm not really sure what the purpose of Q is, but whatever. And box this guy off. Over here, we're going to have a really tight hyperbola. And this comes from P all the way down to this unnamed point. You're going to have O cutting into M, passing A. And then up here you're going to have B. That didn't go right. B, no. Bad hand. B. This is a B sub 2. O sub 2. A sub 2. M sub 2. This guy cuts down. Imagine it's a straight parallel line to everything else. Not the hyperbola. This is Q sub 2. Up here we got P sub 2. And box this bad boy off. Such beautiful drawings. And yeah, in discussing the relationships between the corresponding areas, it is convenient to adopt the following use of the word measure. The measure of any area connected with a given central conic is the ratio which it bears to the constant area of the triangle formed by the two conjugate diameters of the same conic. For example, the measure of the sector A sub 1, O sub 1, B sub 1 is the ratio. I'm going to go ahead and draw this. This is going to be the only pretty much equation. So this would be go ahead and get that select tool. Move this bad boy over. May as well make these a little bit easier to denote. So these two guys are together. And we want the sector. We want sector A1, O1, and P1 divided by, these are probably going to be areas, the measure of any area. Okay, yeah. And then we want the triangle A1, O1, B1. So up on top you have going to P, but here we want B. And what that is saying is we want this one is going to be marked with green and red for the other one. So just imagine that I wrote the bottom one in green. Actually, I could probably write that in green. Let's see. Don't really need these. Need a bigger eraser. I don't like Windows. Why did you have to mess up the original paint? May as well go get that Windows XP computer and do this. Anyways, so with green we have triangle A sub 1, O sub 1, B sub 1. So for this example you would have, actually it would go like this. You had this triangle, and then the sector would be between this guy over here, then over here, and then it goes up this way. And so the area would be a measure of the ratio between these two. So you're going to have a certain kind of, with the yeah, so the sector is going to be, I think it's theta. Like you want your area, what is the area of a sector? Because, you know, pi times r squared or something like that, but that's for a circle. There should be geometry in this book. Analytic geometry. Nope. And then again, there's also the hyperbolas. The hyperbolas, there might be something different for getting their actual area, which I think this is kind of what it's getting into, but that's weird. Isn't there geometry in this damn thing? Geometrical progression, no. Analytic geometry. Huh. Mensuration formula. I do not know what that means. Area of a circle. So with a hyperbola, there is an issue here where that section in red is the sector, whereas a circle, you're looking from inside to outside. And while the part where M is, that's not the hyperbole, or the hyperbola. It's between wherever that focal point is up to up there. Maybe it is. I'm not quite sure. Pretty sure the book is going to get into it, but yeah, so if S is the length of the arc, the area of the sector is S times R divided by 2. But that does not work for hyperbola. So you have to somehow figure out the sector and then divide that by the triangle. The measure of any area connected with a certain given central conic is the ratio which it bears to the constant area of the triangle formed by two conjugate diameters of the same conic. So I guess what happens is you end up finding the sector using the numbers that you have. Not sure. Anyways. So this is a measure of the sector. A sub 1, O sub 1, P sub 1 is the ratio and is to be regarded as positive or negative according as A sub 1, O sub 1, P sub 1, and A sub 1, O sub 1, B sub 1 are at the same or opposite sides of their common initial line. Yeah, so we have this. This is Article 1. So Hyperbola, Hyperbolic Functions, Article 1. So that was the first little tidbitty. Now we continue on to Article 2. Areas of corresponding triangles. The areas of corresponding triangles have equal measures for let the coordinates of P sub 1, Q sub 1 be X sub 1 and Y sub 1, and the other point pair is X sub 1 prime and Y sub 1 prime. So what we're talking about is still on select. P sub 1 is equal to the point pair x1, y1. Q sub 1 is equal to x1 prime and y1 prime. And let those other corresponding coordinates P sub 2 and Q sub 2 be equal to the point pair of P sub 2 is X sub 2 and Y sub 2. Whereas Q sub 2 is X sub 2 prime and Y sub 2 prime. Let the triangles P sub 1, O sub 1, Q sub 1, and P sub 2, O sub 2, Q sub 2 be T sub 1 and T sub 2. Let the measuring triangles A sub 1, O sub 1, B sub 1, and A sub 2, O sub 2, B sub 2 be K sub 1 and K sub 2. So let's see. You have T1, that's the triangle for P1, O1, and Q1. T sub 2 is equal to P sub 2, O sub 2, Q sub 2. And then the measuring triangles, you have K sub 1 and K sub 2. K sub 1 is A sub 1, O sub 1, B sub 1, and then K sub 2 is A sub 2, O sub 2, and B sub 2. And then it'll have angles of omega sub 1 and omega sub 2. Then, by analytic geometry, taking account of both magnitude and direction of angles, areas, and lines. So, if you remember, the red is sector, and below is triangle. So here, we're going to have T sub 1 over K sub 1 is equal to, up on here, there's going to be a numerator, and this is 1/2 of x1 times y sub 1 prime. If you notice, this is going to end up looking like the derivative of a quotient, in a way. Not necessarily, but this is going to be minus x sub 1 prime y sub 1 multiplied by the sine of omega 1. The denominator is going to be 1/2. Oh, nope. Getting ahead of myself. A sub 1, B sub 1, sine omega 1. And if you notice, you're going to have some cancellations coming here. You're going to be losing the halves. Then you're also going to be losing the sine of omega sub 1. And this just turns into beauty is in the eye of the beholder. This turns into x1 y sub 1 prime minus x sub 1 prime multiplied by y sub 1 in the numerator. In the numerator, that's what we have above. In the denominator, it's going to be a sub 1 and b sub 1. Pretty easy. Then after this, we have the ratio of t sub 2 and over k sub 2, which is equal to 1/2 x sub 2 y sub 2 prime minus x sub 2 prime times y sub 2 multiplied by sine of omega sub 2. That's in the numerator. In the denominator, you're going to have 1/2 a sub 2, b sub 2, and times sine of omega sub 2. If you were to notice this, so the triangle, let's see, K is over here, the A, O, and B. A, B, and O. That's K. But then T would be POQ. Okay. So P, let me just go ahead and denote that. Okay. Nah, that doesn't work. So K and then T. So O to P to Q to O. And yeah, get that black. So yeah, this triangle, the reason why the K has the sign in there is because you don't know, it's not a right angle. So you're going to be using the base times the height, which are pretty much A and B. You're using the two different sides. This is probably going to be A, and this is probably going to be B, and then you don't know what necessarily what C is. So A, B, that's what's on the bottom. It's what's in the denominator for K, and then you're going to take 1/2 of that because it's a triangle. Ow. If you have a parallelogram, you would just do the multiplication like that, I would believe, without the half. But yeah, you're using like the law of cosines and stuff to get this, and this is just a general triangle formula. On top, though, you have to figure out between the two different points pretty much what the distance is. It seems like you're kind of cheating here. Because, well, not really. You're multiplying x2 by y prime. So if let's see, we're looking for P and Q. So yeah, this bad boy here, that bad boy there, this is going to be Q at, just make that 2, this is 1, come up here, just pretend that those are whole numbers, 3, 2, 1, this is going to be the Y, this is going to be the X. It technically does not matter if you switch them. It only matters if you try and switch them and then plot as if your x's, if x is up here where the y is, and you're plotting x's along the y-axis. Make sure you're plotting the variables and correctly. The convention is just whichever is the dependent variable or the independent variable is the one that goes on the horizontal. If you don't do that, you're just going to freak people out, and that's fine. So this is 1, 2, 3, 4, 5. So 3, 5 for P. And then Q is, it looks like 2, 1. So this triangle, 1/2 of x1. X1 is, the primes are in Q. So this is 3. Okay, so you're multiplying by the sine of omega, which is probably coming from O, times that prime. That'd be 1 minus sub 1, x sub 1 prime, which is 2, and then y sub 1, which is times 5, sine omega 2, or no, omega, because I don't know which P and Q these are. So 3 minus 10, that would be minus 7. So negative 1/2 times 7 times sine omega divided by whatever A and B are. So you could have it like right here and right here. But you also need to find out what the A and the B are. Anyways, therefore by 2, I guess this might be article 2, I'm not sure. Oh, 2, okay. That would be the original kind of thing where it was, if P1, P2 are situated such that x1 divided by a1 is equal to x2 divided by a2, and y sub 1 divided by b sub 1 is equal to y sub 2 divided by b sub 2. That would entail using this. This was labeled as 2 in the book. The guys over here, this was actually 1. And this ends up turning into x sub 2, y sub 2 prime minus x sub 2 prime, y sub 2. And this is, that would be in the numerator. The denominator is going to be a sub 2, b sub 2. So using 2, don't like that. Don't like that. Don't like that. I'm going to be here all day. This turns into t sub 1 over k sub 1 by 2 equals t sub 2 divided by k sub 2. And this would be, I guess, equation set 3. not particularly feeling it. I think 2 articles from this is fine. Hope this has been enjoyable for you, especially hearing a little bit of my frustration. Possibly. Who knows? But yeah. Hyperbolic functions. These things get kind of crazy, I guess. It's kind of useful knowing what the hyperbolas do. What's the use? Catenaries. Like if you have so let's say that you have this stick over here, like a post, and a second post, and you want to take a line, like a chain, and put it like that, just straight across. Well, what's going to happen is, due to gravity, it's going to shape like a parabola. Or not parabola, hyperbola. Parabola, hyperbola. And with this, it's called catenary. You're going to end up having kind of like a focal point here, and just like these other guys, you have all kinds of stuff, and you're going to want to take this down like possibly here, and then you want to know what the sector is. Interesting. This does not look like it says erase. It definitely did not erase anything. That's cool. Huh. No, that's still erase. Oh. Oh, I have to have it. What the? That does not work. Whatever. But yeah. You're going to be able to find a sector like this, kind of. You're going to want to know probably, like, if you want to know where it's actually tangent parallel to the ground, it would be right there. Maybe you want something to go up this way. And, you know, you have your tangent there, tangent here, tangent here. That's a circle. Pretty much everywhere it's moving. So such a tangent would be if you have a curve or a circle, you want it to only touch in that one spot. And nothing else. Of course, if you want to take the tangent to a straight line, it's a straight line itself. Whether it's horizontal, vertical. A vertical line, the tangent it's vertical. Horizontal, it's horizontal. And so if something's tangent to it, it's because it kind of just barely grazes the topic, but then it goes off into a random direction. Yeah. You have a post, second post, you attach something between it, and it turns into a catenary. And that's a use of hyperbolic functions, an applied set of that. But besides that, this is article 2 that I finished, so enjoy. Ciao.